welcome to our podcast. Today we're diving into a fascinating development in molecular dynamics simulations involving force fields. Let's get started.
I'm really excited about this topic. What's the main breakthrough we're discussing today?
Well, it's about a new method for simulating chemical reactions and mechanical properties at the atomic scale. You know how challenging it is to model these reactions accurately, right?
Absolutely. It's been a long-standing issue in materials science.
Exactly. So, the researchers introduced a method using a reactive force field called IFF-R, which replaces non-reactive harmonic bond potentials with reactive energy-conserving Morse potentials.
Wait, so they're using Morse potentials instead of harmonic potentials?
Yes, that's right. The Morse potential allows for bond dissociation in simulations, which wasn't possible with traditional harmonic potentials.
That's a big deal. How does IFF-R compare to existing force fields?
Well, it's compatible with popular force fields like CHARMM, PCFF, OPLS-AA, and AMBER, so you can integrate it without overhauling existing setups.
That's convenient, but does it maintain the accuracy of those force fields?
Yes, it does. That's one of the key points. IFF-R maintains the accuracy of the corresponding non-reactive force fields while enabling reactive simulations.
That's impressive. So what kind of reactions can it simulate?
It's capable of simulating bond breaking in molecules, failure of polymers, carbon nanostructures, proteins, composite materials, and even metals.
Wow, that's quite a range. How does it handle bond formation?
They include bond formation via template-based methods. So you can simulate both bond breaking and forming in your models.
That's really useful. But I'm curious, how does the performance compare to prior methods?
Oh, here's the exciting part. IFF-R is about 30 times faster than previous reactive simulation methods.
No way! 30 times faster? That seems a bit optimistic. Are they comparing it fairly?
Yes, they've benchmarked it against Reactive and other common methods by using Morse potentials, which are more computationally efficient for modeling bond dissociation.
But doesn't simplifying the potential risk losing accuracy?
That's a valid concern, but they maintain accuracy by keeping the rest of the force field parameters the same as in the non-reactive versions.
All right, that makes sense.
Definitely. It's like having a high-speed highway for simulations that was previously a bumpy dirt road.
Haha, that's a great analogy. So, are there any use cases they demonstrated?
Yes, they showed applications in bond breaking and failure mechanisms in various materials, like polymers, carbon nanotubes, and even metals like iron.
Metals too? But aren't metals usually tricky to model reactively?
Exactly, but with IFF-R, they managed to simulate ductile failure in G-iron.
Impressive. I'm curious, does this method have any limitations?
Well, they acknowledge that simulating complex reactions would still require more detailed methods or assumptions. So while IFF-R advances the field, it's not a silver bullet for all reactive simulations.
Got it. So it enhances efficiency and maintains accuracy while expanding capabilities?
Exactly. It's a significant step forward in materials modeling.
Definitely. I can see this being adopted widely in the community.
Absolutely. The fact that it's compatible with existing force fields means researchers can integrate it into their work easily.
Right. You mentioned that the Morse parameters are interpretable. Can you explain that?
Sure. The Morse potential uses 3 parameters per bond type: the equilibrium bond length, the well depth, that's the bond dissociation energy, and a parameter related to the bond stiffness.
I see.
These parameters can be obtained from experimental data or high-level quantum calculations.
That makes sense. So it's grounded in physical reality.
Exactly. And because of that, IFF-R maintains the accuracy of the force fields it's based on.
That's key. This seems like a practical solution to a long-standing problem.
Definitely. It's exciting to think of the possibilities this opens up.
Yeah, but what about complex reactions involving multiple steps?
Well, they mentioned that simulating those would still require more detailed methods or assumptions.
Right.
So while IFF-R advances the field, it's not a cure-all for every reactive simulation challenge.
Fair point, but it's still a significant advancement.
Absolutely. It's a substantial improvement in terms of speed and applicability, and it could greatly facilitate research in materials science.
One thing I'm wondering is how user-friendly it is.
They develop tools and scripts to help implement IFF-R, so it should be accessible to researchers familiar with molecular dynamics simulations.
That's good to hear. I imagine computational chemists will appreciate that.
Indeed. And given the compatibility with existing force fields, it's like adding a new feature to your current toolbox.
Exactly. Well, this has been a great discussion.
Agreed. I can't wait to see how IFF-R impacts future research.
Same here. Should we wrap it up here?
Yeah, I think we've covered the main points. Thanks for the engaging conversation.